Okay, continuing on with our last example, example 6, y equals r sine of theta. Our r is 2 plus 2 cosine of theta, and then times sine of theta. So that's your r sine theta. Well, for both of these expressions of x and y, we're going to take derivatives. dx d theta, well, use the product rule. We've got our first function, 2 plus 2 cosine of theta, times the derivative of the second, which is negative sine of theta, plus, well, now we're going to take the derivative of our first function. First here is going to be negative 2 sine theta times our second function, which is cosine of theta. While we're at it, let's distribute negative sine of theta to both terms inside of here. And you might notice also, after we've done that, we're going to be able to combine some like terms. This is going to be negative 2 sine of theta minus 4 sine of theta cosine theta. That is dx d theta. Coming over here, we're going to do the same thing, dy d theta. Well, we're going to take our first function, 2 plus 2 cosine of theta, times the derivative of sine, which is cosine of theta, plus taking the derivative of the first function now, and again, that's going to be negative 2 sine of theta. Multiply that to our second function, which is sine of theta. And again, let's do the same thing. Let's distribute. We'll get 2 cosine of theta plus 2 cosine squared of theta minus 2 sine squared of theta. And that, of course, is our dy d theta. You might notice that, sadly, we don't have a nice, simple combining of like terms that we can have like we had before. But I do want to call something out here. This problem is not asking us specifically to write the formula for the derivative dy dx, but it might help us to do so. Look, this is just going to the top of the notes. It's dy d theta, which of course is 2 cosine of theta plus 2 cosine squared of theta minus 2 sine squared of theta, all over our dx d theta, which is a little bit simpler looking. We have negative 2 sine theta minus 4 sine theta cosine theta. Well, the question at hand is actually for us to find the points at which the tangent line is horizontal, find the points at which the tangent line is vertical. Well, what that means is if we looked at where our tangent line is, say, vertical, for example, we'd like for dx d theta to equal 0, the denominator to equal 0, and our top, our numerator, to not be 0. So tell you what, let's just go to dx d theta and set that equal to 0 and solve this equation. And by the way, what we can do incredibly fast is factor out a negative 2 sine of theta. That's going to leave us with 1 plus 2 cosine of theta. Set both of these factors equal to 0. And right here we get 1 plus 2 cosine of theta is equal to 0. This second equation that I just finished writing is cosine of theta is equal to negative 1/2. This would be equivalent to sine of theta is equal to 0. And let's solve, realizing trig functions are periodic, sine and cosine at least are periodic, about 0 to 2 pi. Where is sine equal to 0? Well, at 0 itself, at pi. Lots of times kids might say, well, what about 2 pi? Well, remember, we're not including 2 pi here, so we'll just stop with those two. What about cosine? Where is it negative? Well, all students take calculus. Cosine is negative in the second and the third quadrant. With a reference angle of pi over 3, you could quickly come up that theta would be 2 pi over 3 and theta would be 4 pi over 3. These are all angles in radians for which our denominator would be 0. Now, we do have to carefully check through what's happening with our numerator. Our numerator, dy d theta, we're going to set equal to 0 as well. And we could type this in as a function, change our calculator back to function mode, type this in and solve for where our equation would equal 0. And that's fine. You can certainly do that. But let's also talk about how to solve by hand. If you factored out a 2, you'd have cosine squared minus sine squared, which, by the way, is really cosine of 2 theta. So really pulling back some trig. And my goodness, cosine of 2 theta actually has yet another identity to it. You might remember there were 3 identities for cosine of 2 theta. And right now I'm going to use another one that hopefully will be obvious. This is also equivalent to 2 cosine squared of theta minus 1. So, by the way, what you could do immediately is divide everything by a 2, since we're dealing with an equation that we need to solve here. 0 is equal to, well, let's just reorder everything. 2 cosine squared of theta plus cosine of theta minus 1. And my goodness, do you know where we're headed? This will factor. Factoring into 2 cosine of theta and cosine of theta. You might guess that we'll need a 1 and a 1. Let's make this a plus, make that a minus. You'll see that that does factor out. 2 cosine of theta minus 1 equals 0 leads us to cosine of theta equals a half. More simply, cosine of theta plus 1 equals 0 leads us to the cosine of theta equals negative 1. So where are we going with this? Well, theta could equal pi for the cosine of theta to equal negative 1. Cosine being positive 1/2, well, this will be going back over here into the first and in the fourth quadrants. So theta would be pi over 3, and theta would be 5 pi over 3. So you know what? We found all of these angles for which the numerator and denominator could equal 0, but there's one huge significant problem. And the problem is this: theta equals pi. In other words, when theta equals pi, we're seeing that dx d theta and dy d theta would both simultaneously equal 0. So in other words, going back to the top of our notes, the case 0 over 0 requires further investigation. You know, that's the one problem that we're going to have here. And tell you what, I'm going to just drag this derivative down. It's a good reason why we wrote this out over here. We can bring this down a little bit. And let's investigate what's happening when this derivative is going to be approaching, having theta approach pi. Obviously, we get 0 over 0. So, in fact, if I may, I would like to change this problem a little bit, just for the sake of time. And I tell you what, I'm going to erase all this. I'm going to say what's happening with this derivative as theta approaches pi. Well, do you know what? We get 0 over 0. We can use L'Hopital's rule. And because that's the big question. We'd really like to know what exactly is happening when theta is equal to pi. or approaches it. So take a derivative. Obviously we get 0 over 0, but the derivative of cosine is negative sine, so this is 2 negative sine of theta. Here we're going to need the chain rule. 2 brings down with the 2 to multiply a 4. It's 4 cosine of theta, but take the derivative of the inside, we'd get negative sine of theta here as well. And then doing yet again another chain rule over here, bring down the 2, we'll have minus 4 sine of theta times the cosine of theta. Well, down in our denominator, taking that derivative, negative 2 sine of theta, well, that derivative becomes negative 2 cosine of theta. And if we're really on our toes right now, we're going to notice something really good happening. I'm going to leave this negative 4 out. This would be sine times negative sine of theta with the product rule. And then we could say plus, well, the derivative of sine is cosine, and then we'd have another cosine over here. But look, when you plug in a pi to the top, sine of pi is 0. So my numerator is going to be 0. Down below, cosine of pi is negative 1. That's a 2. And I can tell you right now that this is not 0. Down below, 0 divided by something that's not 0 is 0 itself. So do you know what? Our top is 0. We're not undefined. This is going to be a horizontal tangent. Horizontal tangents occur when we have our numerator equaling 0 in our derivative, but our denominator is non-zero. We come back over here, we're going to throw out that pi. These other 3 theta values are going to correspond to a vertical tangent. So, one other issue to quickly talk about. Okay, that last thing to talk about, of course, is going to be which ordered pairs are actually showing up for these vertical tangent lines and horizontal tangent lines. To know that, we'll do this real quickly. Just look at the top once again. Your x and your y were actually written out with formulas right here. And same thing right over here. So what we can do is substitute those angle measures in for x and y, and then we'll be good to go. So just finalizing this, again, you can confirm this on your own real quickly, but I'm not going to show all of the work that corresponds to that. But vertical tangent lines. We have vertical tangent lines when we had theta was equal to 0, theta was equal to 2 pi over 3, theta was equal to 4 pi over 3. Well, if you plug those angles into the formulas that we highlighted up there, we'd have the ordered pair Cartesian x comma y, 4 comma 0, negative 1/2 root 3 over 2, negative 1/2, comma, negative root 3 over 2. We also have horizontal tangent lines. That's where our numerator is 0 and our denominator was not 0, where dy d theta was 0. We saw that, and we even needed to use some extra work to figure out that at pi, that was the case. At pi over 3, and also 5 pi over 3. Well, we could very quickly do some work at pi. That's going to correspond to the pole, 0, 0. We're also going to have at pi over 3, 3 halves, and then 3 root 3 all over 2. Finally, at 5 pi over 3, we'll have 3 halves and negative 3 root 3 all